It's coming in, it will pass behind the sun in October. James Webb is observing it right now, or just a couple of days ago was observing it.
The James Webb Space Telescope spotted a large object about 10 light years away moving toward Earth.
On July 1st, 2025, telescopes spotted a colossal interstellar object, 3I Atlas, racing through our solar system at 13,000 miles per hour. What's baffling scientists is its behavior. It's exhaling massive carbon dioxide plumes, yet remains completely unmoved. Despite jets powerful enough to form a glowing tail millions of miles long, its immense mass keeps it steady. Believed to be billions of years older than our sun, this ancient traveler may hold secrets from the early Milky Way, and time is running out to uncover them. The discovery.
3I Atlas comes back into view. Right now, it is hidden behind the sun, and during its closest approach, Earth-based telescopes are not going to be able to see it. What's worse,
on July 1st, 2025, telescopes in Chile belonging to the Atlas survey noticed a faint, fast-moving smear of light. It seemed ordinary at first, probably just another small body beyond Jupiter, until orbital calculations revealed something astonishing.
You're looking at a piece of what would have become a planet in another star system.
It was an interstellar object, and worse, it was alive. It showed unusual comet activity, much more intriguing than the scientists were used to. In fact, it was on a hyperbolic trajectory, not bound to the sun. That means it was not from our solar system.
there's a mysterious interstellar object hurtling towards our solar system, exciting scientists across the globe.
Soon, a global network of telescopes, including Hubble, Webb, and others, turned their gaze toward this interstellar wonder. Webb's moment came on August 6, 2025, when it trained its near-infrared spectrograph on 3I Atlas. When Webb observed 3I Atlas in infrared, it pierced through the dust and gas, revealing molecular fingerprints that even optical telescopes can't see.
We'll pick out objects that are moving inside of the four frames, and we have to identify if they are real or if they are false detections.
Webb then confirmed the presence of carbon dioxide, water ice, carbon monoxide, water vapor, and carbonyl sulfide in the comet's coma and in the gases leaking from it. One of the most striking revelations, however, is that the ratio of CO2 to water in 3I Atlas is unusually high, far higher than in most comets from our solar system. Scientists knew that this could only mean one thing: the comet must have formed in a colder, carbon dioxide-rich region, or been exposed to intense radiation over cosmic time, leaving behind a crust that suppresses water release.
The plume of gas around it is mostly carbon dioxide, 95% by mass, based on the Webb telescope data.
Because carbon dioxide is easier to vaporize than water ice under solar heating, it can dominate the gas emissions, creating a strange kind of steam around the comet. In effect, 3I Atlas seems to be breathing CO2 as it moves past us. And even before Webb's observations, Hubble had already taken stunning images of 3I Atlas.
We've got some fresh images of 3I Atlas, a third ever interstellar object observed from Earth.
On July 21, when it was about 277 million miles from Earth, Hubble captured a teardrop-shaped cocoon of dust trailing off the nucleus, showing that the comet was actively shedding material. Now, that cocoon is not a static halo. As the comet approaches the sun, heat causes ices on or near its surface to sublimate and turn from solid to gas. Those gases drag dust grains with them, forming the glowing coma, a dust tail, and sometimes even localized streams where more volatile ices erupt suddenly.
This comet's really cool because it does have that tail from the sun's radiation blasting it, but it also has a forward-facing tail.
But experts were astonished to find that Atlas actually has behaviors unlike typical comets of our solar system. Its CO2-dominated outgassing pattern, its suppressed water vapor relative to CO2, and possible insulating crust all hint at a more intense history.
This is something that we didn't realize before. And they also move without creating an exhaust or breaking the sound barrier.
If the circumstances were normal, it shouldn't cause this much talk because it happens to be the third confirmed interstellar object ever detected. After 1, Oumuamua in 2017, and 2, Borisov in 2019. What makes 3 Atlas especially thrilling is that it might be the largest and oldest interstellar body we've ever seen. Some estimates put its diameter to about 7 miles, which is unusually massive for its kind. Now, because Webb's data can tell us about its molecular composition and release mechanisms, scientists hope to compare them directly to comets formed inside our own solar system.
This is the trajectory right here. It's kind of close to Mars, but not really, but it's still pretty far away from Earth.
That could uncover details about how other planetary systems form, how volatile chemicals behave in space, and even how ancient parts of galaxies evolve. As 3 Atlas races inward, it will pass behind the Sun in late 2025 and eventually swing back out past Jupiter in 2026. Until then, telescopes across Earth and space are locked on it, racing to decode every plume, gas, and dust trail before it vanishes forever. New insights into the interstellar visitor. If we're talking age, 3 Atlas isn't just old. It might be ancient. Some astronomers believe it could be billions of years older than our Sun itself. Using models that trace its journey through space, researchers followed its path backward almost 4.7 million years, and nothing nearby could explain where it came from. That means this comet probably didn't start its story anywhere close to our solar system.
How amazing is it that we humans have a word for something that literally flies between stars and so far?
Instead, it likely formed in a distant, ancient part of the Milky Way, somewhere between the galaxy's thin and thick disks. That's a region filled with some of the oldest stars ever born. This tells us that 3 Atlas could carry the raw material of early galactic history, that is, dust and ice that have been floating in space since before our Sun even existed. Now, here's where things get even more interesting. Astronomers studying how light bounces off the comet, what they call polarization, found something unusual.
We're getting an unprecedented data set, not just of galaxies, but of variable stars and near-Earth objects as well.
Usually, when sunlight reflects off a comet, it follows a pretty standard pattern. But 3 Atlas didn't behave that way. The light coming from it showed a deep, narrow negative polarization when the viewing angle was small. The dust and ice around it are unlike anything seen in normal comets. It's likely made of a mix of bright, icy grains and darker material, which gives it this strange optical fingerprint, different even from 2 Borisov, the last interstellar comet we studied. Then, when scientists observed its brightness in early July 2025, something surprising showed up. It was calm. No big explosions or flashes like other comets sometimes show. A few bright spots appeared, but when checked carefully, they turned out to be due to background stars or atmospheric interference, not the comet itself. So, 3 Atlas is active.
From images, we also saw that this object is active, which is an indication that this object is in fact a comet.
Yes, but there's another puzzle too. Its massive size. Comets usually feel a small push when gas jets burst out of their surface, a sort of natural rocket effect called non-gravitational acceleration. But with 3 Atlas, astronomers couldn't detect any measurable push at all. That suggests this thing is really heavy. Even though it's venting gas and dust, the force barely moves it, based on its motion. They estimate the solid core or nucleus could weigh tens of billions of tons and measure over 3 miles across. As it travels closer to the Sun, its behavior also changes. When it was far away, Most of the light we saw came from scattered dust. But once it moved within about 3-point astronomical units, which is roughly the distance between the Sun and the asteroid belt, the pattern shifted, indicating more icy grains were being released. That change affects how bright, transparent, or reflective its surrounding coma looks.
We cannot really pinpoint the nucleus size. It's partially due to the size of the object, but also it's partially due to the activity.
Spectral readings even show cyanide and nickel emissions. These are gases that reveal what's hiding inside the nucleus and how it reacts to sunlight. These findings hint that as 3I Atlas warms up, new layers of its ancient chemistry start to wake up. Though data is still coming in, newer surveys like those from the Rubin Observatory suggest that 3I Atlas could be one of the largest interstellar visitors we've ever seen. If those size estimates hold up, around 3 miles or more in diameter, it raises a big question. How many other giant ancient travelers are drifting between the stars, just waiting to be found? 3I Atlas, compared with its predecessors. 3 interstellar visitors have entered our solar system so far, all from beyond the Sun's reach. First came one I Oumuamua in 2017, then 2 I Borisov in 2019, and now, in 2025, 3I Atlas.
This is the first time something like that is observed, where there is a glow ahead of the object towards the Sun.
Each one has taught astronomers something new about how objects travel between the stars, and each has challenged what we thought we knew about comets and asteroids. Oumuamua was strange from the start, small, fast, and seemingly inert. It was estimated to be about a mile in length, elongated like a giant space cigar.
It was the very first object that we had ever discovered that had originated outside the solar system.
It lacked the visible features of a comet. No clear coma, no visible tail, practically no detectable gas or dust emissions, at least not as we normally expect.
And in fact, it's not just rotating, it's tumbling. So it's not just it's going end over end, but twisting as it does so.
It also moved with a hyperbolic orbit, showing non-gravitational accelerations, which hinted that something was probably pushing on it, perhaps outgassing. But surprisingly, little evidence of what gas or volatile material might be doing so. Then came 2 I Borisov, a more familiar sight in many ways.
Observing this rare comet that had water vapor in it.
Borisov had a coma and tail. It produced gas and dust. It behaved chemically more like the comets in our solar system. Its size was larger than Oumuamua, estimates around 0.62 miles in diameter. Its speed was interstellar, its eccentric orbit clearly unbound, but in composition and appearance, it felt more comet-like in the traditions we know. We could analyze its water, carbon monoxide, some radicals like CN and dust, getting a fairly good sense of the chemistry of an interstellar comet. Now, 3I Atlas enters and raises more questions because it shares traits with both, but also diverges in big ways.
It's easier for me to think this is a new kind of object that requires way more study than we've given it thus far.
Speed-wise, it's among the fastest of the 3. Observations place its hyperbolic excess velocity, its speed relative to the Sun at nearly 13,000 miles per hour, faster than Borisov and much faster than Oumuamua. In terms of size, 3I Atlas definitely dwarfs the others. Early estimates of its diameter go up to several miles. Reports say as much as 6 miles or more, depending on how much dust from its coma is affecting the brightness.
The comet is here, the Sun sends the solar wind to the comet, the tail goes behind the comet.
If those estimates hold, then it's significantly larger than Borisov, and many tens of times larger than Oumuamua. Compositionally, 3I Atlas behaves like a real comet, in the sense it has a coma, dust, visible activity, and gas emissions that we can detect.
This comet is at the reverse side.
But is it nature or something else? We're going to find out soon.
So in that way, It's more like Borisov than Oumuamua, which was puzzlingly inactive, or at least nearly invisible in the usual gas or dust signatures. However, the detailed mix of gases, how active it is, how its brightness changes, are still being worked out. And there are hints of oddities, ratios of volatile compounds, the behavior of dust and ice grains. What makes scientists especially excited is that 3I Atlas might tell us more than just another data point. It may bridge gaps. Oumuamua taught us that interstellar objects can be weird, doing things we didn't expect, perhaps without obvious gas, or with shapes or accelerations that defy simple comet/asteroid categories. Borisov showed that some interstellar visitors are classic comets. Water, dust, volatile behavior, things we recognize. But with 3I Atlas, we might get deeper insight into the range of possibilities, how big such objects can be, how old, how varied the compositions, how durable. Because 3I Atlas is larger, it remains observable longer. Its coma gives more material to analyze. Because it's faster, we get higher energy entry, maybe better clues about how it was ejected from its home. Also, its orbit has higher eccentricity, making its interstellar origin more certain and extreme, which means any data we get may probe conditions far outside our solar system's norm. It may even trace back to very old, metal-poor stars or galactic regions we haven't sampled well before. In short, 3I Atlas is similar in that it is, like the other two, interstellar, with a hyperbolic trajectory and offering rare glimpses of material from distant star systems.
This object has just been discovered. 3I Atlas was discovered on July 1st by the NASA-funded Atlas survey.
But it's different in scale, in speed, in observable activity, and possibly in age and origin. It holds promise to teach us more because bigger, more active interstellar objects let us collect more light, more chemical signals for a longer time. That means more precise measurements, more robust conclusions, and perhaps revision of our ideas of how interstellar objects form, survive, and travel. If Oumuamua was the enigma and Borisov the confirmation, then 3I Atlas may be the revelation, one that nudges us toward understanding not just a few wayward rocks, but the population of interstellar comets that sweep through our galaxy, invisible until we get lucky. The only thing is, 3I Atlas is making it quite difficult for us to gather enough data for every hanging question to be answered. 3I Atlas is making it hard for us. One of the biggest challenges is that 3I Atlas is moving really fast and is very faint. Because it comes from outside the solar system, it has a hyperbolic excess velocity of about 37 miles. That kind of speed means its position in the sky shifts quickly. Telescopes have to track it precisely, or they either miss it or blur it. Adding to that, it's faint, far beyond what small telescopes can easily see. Many observations have to rely on stacking images to increase the signal enough to detect the object. Test data, for example, required image stacking to recover 3I Atlas when it was very faint in the days before discovery. Another limit scientists have faced is the crowding of the sky. 3I Atlas has been observed in parts of the sky near the galactic plane, where so many stars are in the background that distinguishing the comet's light from background stars is hard. This so happens that spectroscopy and imaging both suffer contamination from field stars. For example, when using MUSE or other instruments, observers had to use special techniques so that background stars and artifacts didn't swamp the faint signal. Moreover, the temporal window, that is, the time we have to observe it before it becomes too faint, too close to the sun, or disappears in glare, is very constrained. 3I Atlas is approaching perihelion, which typically is when comets are most active, and yet for 3I Atlas, that perihelion happens when the object is on the opposite side of the sun from Earth at times, or very close to the sun's line of glare. Observations during that period are nearly impossible, because telescopes on or near Earth can't point too close to the sun, and the sun's brightness makes the object essentially invisible. Also, Once the object recedes again, it fades, gets smaller in apparent size, and its coma becomes more diffuse, all making detection and measurement tougher. Instrumental limit is also a major issue. Basically, how much detail our tools can see. A telescope's resolution depends on its size, the steadiness of Earth's atmosphere, and how sensitive its detectors are. If the telescope isn't large enough or the sky isn't steady, the image becomes blurry, and we lose all the fine details. Another problem is that the gases scientists look for don't show up strongly in visible light when the comet is far from the sun. That's because sunlight at that distance is too weak to make those molecules glow, and there aren't many molecules to begin with. So even powerful telescopes might detect little or nothing at all. When scientists try to use instruments that see infrared light, like X-shooter or GTC, the data often becomes noisy or unreliable because Earth's atmosphere absorbs some of that light.
2023 DZ2 was a significant asteroid. A rock that size might only happen a handful of times per century.
This telluric absorption makes certain parts of the spectrum hard to read or even useless for measuring specific gases. The signal-to-noise ratio is also another big obstacle. If the comet's light or signal is too faint compared to the background noise from the sky, the detector, or even moonlight, the data becomes unclear. To fix this, astronomers take longer or multiple exposures, but that only causes new problems. The comet moves across the sky, and if it moves during a long exposure, its image blurs. Bad weather, clouds, or bright moonlight can make things worse. Even studying how the comet rotates is hard. The bright, fuzzy cloud of gas and dust hides the solid nucleus, making it almost impossible to detect brightness changes that show rotation. Some telescopes, like SOAR, only found flat light curves, meaning no visible variation. Finally, there are timing and targeting issues. Some important wavelengths can only be seen from space, but space telescopes have tight schedules. On top of that, early orbital data for 3I Atlas wasn't perfect, so even a tiny mistake in its predicted position could make a telescope point to the wrong spot. Can Juno help us? Because 3I Atlas is only the third confirmed object ever detected from beyond our solar system, scientists are eager to learn as much as possible about it. Recently, a group of researchers proposed a bold idea: to use NASA's Juno spacecraft, which is currently orbiting Jupiter, to try and intercept 3I Atlas as it passes by.
Of one of the most mysterious planets in the universe, and now NASA is right there in Jupiter's orbit.
The plan would involve changing Juno's speed by about 1.8 miles per second, a big but potentially achievable adjustment. This maneuver, called an Oberth maneuver, would use Jupiter's gravity to give Juno a powerful boost, allowing it to line up with the path of 3I Atlas by early 2026. If it worked, Juno could perform a flyby, meaning it would pass close enough to collect valuable data, like images, composition readings, and measurements of the object's surface and gases. These direct observations would offer insights that telescopes on Earth simply can't capture. Although this mission idea is still just a proposal and hasn't been approved by NASA, it's an exciting example of how scientists are thinking creatively, using an existing spacecraft to study one of the rarest cosmic visitors we've ever seen. That spacecraft is Juno, a machine built to explore Jupiter, but one that might now be asked to take on a brand new challenge. Juno began its journey from Earth on top of an Atlas V rocket, headed toward the largest planet in our solar system. It finally reached Jupiter in 2016, after traveling nearly 5 years through deep space. Juno was designed for one main goal: to uncover the secrets hidden beneath Jupiter's thick, swirling clouds.
This is the view from Juno's approach to the largest planet in our solar system.
Before Juno, most of what we knew about Jupiter came from telescopes and earlier flybys by spacecraft like Voyager and Galileo. But Juno changed the game. It went into orbit around Jupiter, circling the planet again and again, collecting close-up data that no other mission had ever gathered. Juno isn't your typical metal and wire satellite. It's roughly the size of a basketball court, with 3 huge solar panels stretching out like wings. These panels are crucial because sunlight at Jupiter's distance is about 25 times weaker than on Earth, so Juno needs all the surface area it can get to generate enough power. Inside, it carries a collection of sensitive instruments, cameras, magnetometers, plasma detectors, and even a microwave radiometer that can peer through Jupiter's clouds, measure its magnetic field, and detect what's happening deep within its atmosphere. One of the most surprising things Juno found is that Jupiter's interior isn't as uniform as scientists once thought. Instead of having a neat, compact core, Jupiter may have an unusual core, a mix of gas and heavier elements swirling together.
And at the center of this mission, NASA hopes to figure out exactly what Jupiter is made of.
Juno also discovered massive cyclones at both of Jupiter's poles, each larger than the size of Earth, moving in beautifully organized patterns. Its high-resolution camera, JunoCam, has given us stunning images of Jupiter's storms, colored bands, and auroras glowing at the poles. But what makes Juno so interesting in the case of 3I Atlas is where it is and how it moves. Since it's already in Jupiter's neighborhood, it's uniquely positioned for a possible intercept. Jupiter's immense gravity could be used to slingshot Juno, giving it a boost of speed through what's called an Oberth maneuver. In simple terms, this means firing Juno's engine while it's deep inside Jupiter's gravity well, so it gains much more energy than it would elsewhere. Think of it like swinging on a rope and letting go at just the right moment. You get flung outward with extra speed. If this daring plan were carried out, Juno could use that gravitational boost to aim itself toward 3I Atlas as the interstellar object zips past Jupiter in March 2026. It wouldn't be able to slow down or land, but even a brief flyby would be scientifically priceless. Juno could snap pictures, measure the object's composition, and detect any trace gases or dust trailing from it. Since interstellar objects travel at incredible speeds, every second of observation would count. Of course, there are challenges. Juno wasn't designed for this kind of chase mission, and by 2026, it will have been in Jupiter's harsh radiation environment for nearly a decade. Its systems are aging, and its fuel reserves are limited. The proposed trajectory change would require precise timing and a significant amount of energy. Still, scientists argue that the potential rewards, getting our first close-up look at an object from another star system, make the risk worth considering. Even if NASA decides not to proceed, the idea itself is inspiring. It shows how much ingenuity scientists can bring to the table, repurposing a spacecraft designed for one mission to potentially answer questions about an entirely different mystery. Juno has already rewritten what we know about Jupiter. If it gets the chance, it could also become the first human-made object to meet a visitor from another star.